Okay. Did everyone else get notified that it was being recorded?
Yes.
Okay. All right. Well, good morning, good afternoon, good evening, wherever you're joining us. Thank you for joining as we continue on in our 2024 ISAR Virtue Aeolian seminar series. Philippe Claudine, Andrew Gunn, and Jean Bernard and myself, along with the entire ISAR board, are excited to continue this series. This is a three-part series that's building on the exciting results from ICAR. And we wanted to elaborate on some of the open questions and directions for future research. So finishing this three-part series today, we have Dr. Cheryl McKenna Neuman and Dr. Joe Nield. Before I turn it over to Philippe to introduce our speakers, here's the structure of today's webinar. So please keep your microphones off unless you're called on in the end during our Q&A session. But please feel free to type questions in the chat at any time. That way we have a nice list of questions lined up as when our speakers are done. But feel free to, we're gonna wait till the end to read them. And Jean-Bernard, Philippe, and myself will take turns reading them to our speakers. If you prefer just to raise your hand as well to ask your question, that's totally fine too. This meeting is being recorded and will be shared with the ISAR community. So we ask that everyone contribute to creating and maintaining a welcoming and respectful work environment that fosters diversity, inclusion, and belonging. And now I will turn it over to Philippe. Thank you.
Okay, welcome everyone. It's a great pleasure. So today we have a duo, a duet. I don't know exactly how to say this in English, but we have the pleasure to have two speakers. So Joe Nield is an associate professor at the University of Southampton. And so Joe, you are primarily a field person, a field scientist, especially you are a pioneer in the use of TLS to understand the processes in Aeolian environments and the growth and the development of dunes. And you've been traveling a lot in many deserts, especially in the south of Africa, the Namib, and also in the US and also in the UK on the coastal areas. And Cheryl, McKenna, Neuman, you're a professor at Trent University in Canada, and so you've been working a lot on experiments in wind tunnels, but of course you know also you have also a field experience. You know what the field is, and precisely the interest. The great interest of this talk today is to have this dialogue between field studies and experimental studies. How do they connect? How do they interact? And what can we conclude from these different two different perspectives? Thank you.
Okay, are we ready to start then?
Yes.
Okay, all right. Well, we'd really like to thank the webinar organizing committee. It's truly an honor for us to do this today. And in case the audience is wondering, Joe and I have actually collaborated previously in a study of emissions from playa sediment. And this webinar actually gives us a really great excuse to work together again, and we're going to give it very interactively. So I think it's a grand experiment, and we hope that it's as fun for you to watch as it is for us to deliver it. Okay, Joe. Joe is driving the slides today, so you'll hear me saying, "Hey, Joe," a lot. All right. Way back in 1986, about 38 years ago, the Binghamton meeting focused on Aeolian geomorphology that year. And the meeting was actually hosted by our colleague Bill Nickling at the University of Guelph. Now, at that time, I was a young graduate student, and I was actually working in the Arctic. And that's the picture I took of a nice iceberg from a view from my field site. And Joe, incidentally, was still in primary school. Okay. Now, if you looked around the room at that time, you would have seen some very well-known authorities, including highly regarded researchers working in wind tunnels with links to NASA and planetary work, inclusive of Jim Iverson, Bruce White, Dale Gillette, Ron Greeley, Brian Willits, and Rice. So names that are familiar to many of us. And equally somewhat famous field workers such as Chaim Soar, Gary Kosturik, Andrew Gowdy, Ian Livingston, who I understand now is famous for running canal boat tours for Aeolian geomorphologists. And Joe was on last week, so lots of fun. Now, the tricky thing about a lab wind tunnel is that it can be regarded as either an instrument or tool, a hardware model, which is my perspective, or for some, a sad representation of what actually happens in the field. And almost every paper I write ends with some statement to the effect that I hope somebody reads this and I hope somebody finds it useful in regard to model development, validation, parameterization, or calibration. So clearly, my mindset is a connection with the modeling community. And in working on this talk with Joe, I realized that it's now a kind of a shortcoming of my reductionist brain that I never write. I hope that field workers find this valuable and actually invite me to collaborate. So in this talk, we've got sort of three main objectives or focus. We're going to look at some of the advancements and current challenges associated with measuring the sand cloud. There'll be a bit of back and forth dialogue between Joe and I. We're going to examine the progress that we've made in that 40-year span since we first started talking about collaboration and interaction. And finally, we're going to entertain you with a wee bit of backstory on measurement that you're certainly not going to read in a journal article. Okay, next slide. Okay, so this is just an overview of the range of technology available to Aeolian researchers. And it's certainly not meant to be an exhaustive list, but it does show that at a very fundamental level, there's a strong overlap between measurement options for workers in the field and workers in the lab. And basically, these technologies are either involve some sort of physical instrument, such as a sediment trap, or an electronic device that has as its basic principle a response involving optics, acoustics, or a thermal response. Indeed, many of the instruments that we use were initially tested and calibrated in wind tunnels. However, differences can arise from four primary constraints. First of all, some instruments, very simply, are just too big to put in a wind tunnel. So think of a TLS. Joe would love to do that, but you need 8 meters distance. Sonic anemometer. So that's a physical limitation. In wind tunnels, we also use a lot of flow visualization, and it works really well in confined spaces with fog or smoke. But my field experience is that it doesn't work too well in large spaces where the dispersion is too rapid. Also, obviously, some electronic instruments are sufficiently or not sufficiently robust to work in the field, and even some are difficult to work with in the lab. And I've got a lot to say about that. And then some instruments that were developed in wind tunnels will always more or less stay there because they're set up for unidirectional flows. And I'm thinking of pitot tubes, which have been the workhorse of wind tunnel experiments for as long as I can remember. But it's really difficult to put those instruments into omnidirectional winds and get a proper response. Okay, Joe, do you have anything to add to that?
No, just to say, I guess, although we've kind of tried to break them down into different areas, there really is quite an intersect here. So we wouldn't know what speed a cup anemometer was giving us unless we could put it into a wind tunnel first to calibrate it and things like that. So there's a lot of overlap. Even if it might be an instrument that's predominantly used in the field, we still need to have some idea of how it's calibrated first. So in that respect, wind tunnels are vital for any kind of future follow-on field work.
Thanks for that, Joe. It makes me feel validated. All right. Okay. All right, so we're going to move forward now to consider some of the challenges that exist when measuring sediment transport, especially at the intersection of field and lab. All right, next slide. All right, so you're probably wondering what a sandblaster is doing on this side. I didn't have a chilled wind tunnel at my fingertips when I was working the Arctic looking at Aeolian transport in periglacial conditions. So I convinced my supervisor to actually rent me a sandblaster, and I conducted experiments in a freezer in engineering. And it may sound all a bit weird, but it earned me a paper in sedimentology. So I convinced the reviewers that I had something to say. Now, this approach was actually oddly appropriate because sand transport by wind is abrasive. Okay, same technology is used to remove graffiti from walls and things like that in an industry. But the nature of the process actually contributes to very high maintenance costs in my world in wind tunnel simulation. So we're studying effectively what is a fairly destructive process. And that limits what we can do as compared to clean air wind tunnels that are used for studying fluid dynamics and aeronautics. And if you don't believe me, go ask an engineer if you can put wind particles in their wind tunnels. It's no, very hard, no. Okay, and it also limits certain equipment that we can use, like constant temperature anemometry, for example. Hot wire anemometers are pretty frail when it comes to putting them in a sand cloud. However, advances in technology now allow us to measure phenomenon that we only dreamed of about 15 to 20 years ago. But this technology comes at a very high cost. So you can now actually buy a pitot tube anemometer on Amazon on the internet for $70 Canadian, or about the price of a tank of gas for my car. But a laser Doppler anemometer is almost 3,000 times more expensive. So I could buy more than one car. If you build a sediment trap, that probably in materials will cost you about $50 in Canadian currency, but a PTV system is 5,000 times more expensive. So I could fill my driveway with cars, modest cars. Okay, so the key point is that new technologies, which are actually game changers in our research community, are developing faster than we can access resources to purchase them. And with these new technologies becoming more and more resource intensive in terms of capital and time, fewer researchers are able to master the technical skills practiced in both the field and in simulation as they once did. So we're seeing more and more focus and specialization in our work as compared to earlier workers, like, for example, Bill Nickling, who worked very successfully in both the field and the lab for many years. Great, over to you, Joe.
So I guess a lot of the issues that you get in the wind tunnel are the same in terms of equipment. So if we want to use a Wengler gate sensor to look at sediment transport, that's not too expensive, but to buy one TLS, terrestrial laser scanner to look at sediment transport is about 6,000 times more. So similar to issues that we have in the lab in terms of expensive equipment. But I guess there are a few added complications when you're in the field. So it's not just the cost of the equipment. So for example, a sonic 3D anemometer might be 10 times more than a cup anemometer, but it gives you much more data in 3 dimensions, but it's also much bigger. So in terms of getting equipment to remote locations where we want to go measure these things, not only is our equipment more expensive, but it's also larger, which then has a knock-on effect to the cost of getting large bits of equipment to faraway places. And whereas at least in principle in a wind tunnel, you can turn the wind tunnel on and run your experiment, it's not so easy when you're in the field. So there's the added cost of waiting for the wind to blow or not blow. And not only does the sand start to kind of erode and eat away at your hot wire anemometers, but a mouse might come and eat the cup of your cup anemometer or elephant might sit on your tripod and knock down your instrument. So there's a few more hazards involved, I guess, that add to the high maintenance cost in the field.
Okay, so I want to talk a little bit about the nature of the phenomenon and how it drives what we need to measure and where we are in terms of trying to look at things that are rather difficult to do. So even in steady flows in a wind tunnel, in the absence of wind gusts and large-scale eddies that we see in the field, the particle motion can be highly intermittent, especially at low wind speeds around threshold, and highly ephemeral in terms of phenomena like particle ejection or splash and burst. So the faster that we can sample, the more representative the measurements are of natural phenomenon. And a range of technologies now allow for this in sampling at several hundred to even several thousand hertz. And so we've made a lot of really good progress on this front. In the little PTV insert image on the top right-hand side of the screen, we are sampling at about 3,000 hertz, okay? And when we do that, it's quite easy to distinguish the path of the particles. We can visually identify and quantify the difference between reptation and saltation. We can even examine the acceleration of the particle as it experiences fluid drag moving away from the bed surface. And none of this would be possible without the high-speed scientific grade cameras available today. Years ago, we actually pulsed the light sheet. This is what Anne Rice did. We don't do much of that work anymore. And the earlier workers, of course, did a lot of manual analysis of their runs. And it's pretty painful work. But we've got some great tools for this now. Now, if we look at spatial resolution, even in a wind tunnel, it remains a great challenge. We haven't made as much progress with that as we have with sampling very, very fast. So, for example, an LDA, a laser Doppler anemometer, measures at a point within a volume that's about, well, it's less than 1 cubic millimeter. So to measure the flow structure, we actually have to traverse it through a grid while the sampling is asynchronous. But we can get away with that because the free stream we control to be steady through time. And the figure on the lower right actually shows, interestingly, a high correlation in the vertical velocity components of both the air and sand particles moving over the surface of an ornamented bed, in fact. Now, I personally think this is pretty cutting edge work, but if you look at the scale on the bottom, the fetch length is only 15 centimeters. When we run PDV, we're capturing path lengths in the order of a few centimeters or portions of much longer high-speed trajectories. So while we're gaining, looking at the rate at which things happen, it's much harder to push through and get spatial representation. And as a final point, years ago, it was quite common to just put a single pitot tube in a wind tunnel and take a vertical profile and measure U star and then correlate that with the sediment transport rate. And the literature is full of such diagrams and textbooks as well. But we now know that with transport, especially in a very long sedimentary wind tunnel, where we need to have enough fetch to get to saturation, that eventually the flow will become unstable and develop secondary structures. And so we're now starting to try to measure these by looking at different points within the tunnel, but it's slow and difficult work. And again, we can't attain the resolution that we've gained in looking at the rates of transport. Okay, back to you, Joe.
So I guess from a temporal and spatial resolution perspective, fieldwork hasn't come quite as far as the wind tunnel in terms of the temporal resolution. So we're still more or less looking at 1 hertz, 10 hertz, 50 hertz, nowhere near as fast as you can get in the wind tunnel. But I guess the advantage is in the field, you can go much, much, much wider and much longer. So in terms of our spatial coverage, there's potential there to cover a much larger area than you could get in the wind tunnel. But that still presents real challenges. So trying to put enough instruments into that space and capture the spatial and temporal transport and wind dynamics is not trivial and still requires a lot of work. So I'm just going to go through a little bit of an example here to give you an idea of just how fraught with challenges this currently is. So in this example, we're looking at just a simple field setup where we've got a sensor that's buried so that it's level with the ground going up, a Wengler that's 2 centimeters above the ground, and a 3D sonic anemometer that's 26 centimeters above the ground. And these are spaced laterally, if you like, by up to 2 meters. And what we're going to do is just do a snapshot of a 3-minute time period. And why are we doing 3 minutes? Because the laser scanner, if it's measuring a 1 meter by 1 meter spatial area, takes about 3 minutes to cover that area from one side to the other. So on the top line, you can see the wind speed is a little bit higher and then starts to decrease over the 3-minute period. And that corresponds to higher sediment transport counts in our sensor and our Wengler over the first half of the 3-minute period, and then it drops over the second half of the 3-minute period to the point where you can hardly see any measures of transport from the Wengler at 2 centimeters above the ground over the second half, whereas the sensor that's at the ground level is still measuring transport even over that second lower wind speed period. Now, the interesting additional thing that we can do here to try and get at those spatial characteristics and just how important the spatial nature of transport is when you're setting up an experiment and trying to measure it is the use of the terrestrial laser scanner, or the TLS. So in the bottom figure here, what you can see is a heat map of a relative measure of sediment transport based on the backscatter, if you like, of the laser scanner. So yellow is higher amount of transport measured incrementally above the surface. So we're going here from 0 to 6 centimeters above the surface. And then on the x-axis, we're going through time. So you've got the 3-minute time period there. And you can clearly see that during the first half, we've got a lot of transport being detected by the TLS. Most of it is held within the bottom 2 centimeters close to the surface. But in those first 1.5 minutes at least, we're seeing some transport above 2 centimeters. And if you look on the graph directly above our heat map here, that yellow line corresponds to all the transport that the TLS measured that was above 2 centimeters, whereas the red line is everything that measured from 0 to infinity, or probably it only measured up to about 4 meters above the surface, but you get the idea. And you can see there again very clearly, just like the Wengler, the yellow line more or less stops detecting any transport after about 1.5 minutes. So if we were just putting our instrument at 2 centimeters above the surface, we're going to miss that lower transport that you get in the lower wind. That's still there, but most of it is still very close to the surface. So there it's really crucial, I guess, to think about in our experimental designs and what we're comparing to each other. Where have we put our instruments and what exactly are those instruments measuring? So if you were looking at a threshold, for example, at 2 centimeters above the surface with the Wengler, you'd get a different wind speed to if you were putting your sensor that's going from 0 to 1.4 centimeters above the surface. Or indeed, if you're using a TLS, which can get anything from 0 to infinity above the surface. And it's not just the vertical placements that really have an impact on the measurements that you get in the field. It's also how they're spatially distributed in a horizontal direction. So in the top heat map, we can see here, again, we've got 3.5 minutes through time on our x-axis, but now we're looking at width perpendicular to flow. And this is just something very simple, the very maximum height of saltation detected by the TLS through time. And you can see in particular at around 1.5 minutes at about 0.4 meters away from our arbitrary datum here, we've got a very high saltation height detected. And if we had our Wengler positioned at W1, that would detect that potentially. But if we had it at Wengler 2, it would miss all of that transport that we're seeing through time. In the bottom, this just illustrates this more clearly. Here, I've basically just done a sum of all the transport that's going through on that width, so 0 to 1.2 meters through that 3.5 minute period. And you can see there just quite a clear difference if you were at position 3 or position 4 in the transport that you would measure. So it becomes really critical to understand the temporal nature of our transport and the spatial nature of our instruments versus the spatial nature of the transport itself.
Okay. Well, I've spent a lot of time working on morphodynamics in the last several years, basically looking at the interaction between the flow field, the sand cloud, and surface-mounted roughness elements. And I've produced a lot of things that look like the image on the top right-hand side in this sort of work in a visualization sense. And we've been able to measure also very detailed the flow field. But doing this makes one really acutely aware of the flow interference that's created by many of the instruments that we insert into the flow or use in the field during our experiments. And it takes a lot of trial and error, aka experience, to learn how to set up an experiment in order to minimize such interference. We can't get rid of it altogether, but we can try to keep it to a low level. And in fact, it's the #1 problem that I usually flag with students when they set up experiments in the tunnel. And that is bad placement can lead to bad measurements and false interpretations. And that's just a lot of bad. All right. So Joe showed a picture of the Wengler and her field, and here is my Wengler picture. Okay. And basically what we're doing here is we're using LDA gains. So you can see the beams coming across and crossing just in front of the Wengler. And we're profiling the sand cloud and the airflow around this instrument to get some idea of its perturbation, just because it is a physical structure, on what we're trying to measure. Now, perhaps it was a bit unkind of me, but I actually made a PhD student do this before he actually started taking any measurements in the lab and designing his experiments, right? So as a consequence of this problem, particularly in wind tunnels where we've got constricted space, there has certainly been a move towards using contact-free instruments, and that is a lot of optical methods. Even so, we still have some limitations, as Kjeld Rasmussen pointed out a number of years ago with the LDA. We can't get closer than about 4 meters to the surface without some beam interference. PDV gets us right down to the surface in the absence of any perturbation at all. But of course, this field of view is very limited, and we have to deal with enormous numbers of images, and it's really resource intensive. So just for example, if we run a 3-second experiment, which fills the entire onboard memory on the camera, it takes weeks to process. We run a few experiments in a day and we're filling up terabyte drives. And there's a lot of trade-offs to consider with the technology. We still also have to manually calibrate to make sure that our interpretations of the images are correct. It's not for the faint of heart or anyone that has problems with impatience or needs a quick answer. but it is a powerful tool.
So just like in the wind tunnel, we also have issues with instruments and interference in the field, not just the instruments themselves, but anyone that's been on a done field work in a place where it's not in the middle of an isolated desert has probably been frustrated by dogs and tourists getting in the way of instruments, and not just blocking your instruments, but also perhaps destroying your surfaces. And I guess this image that we've got here goes some way to illustrate just some of the issues that we have in both the field and the wind tunnel with placing instruments very close to the surface. So we might want to know exactly what the wind is doing very close to the surface. But as Cheryl said, it's much better to try and do that remotely. So using something like the TLS might give you transport. It doesn't give you wind conditions though. And in this little movie, we're going to see here a protodune forming on our surface, nicely growing through time. And then we put some instruments on top of that protodune to try and measure the wind flow and the transport over that protodune. And very quickly, we get scour around those instruments, and that lovely protodune that's indicated by the magenta dashed line at the start then pretty much disappears and gets blown away due to the interference of the instruments themselves. So these are not trivial things to measure. There's still a long way to go, both in the wind tunnel and particularly in the field, trying to get better remote instruments that aren't going to destroy your surface while you're trying to measure it.
Okay, we're going to move on here and talk a little bit about sensitivity and noise. And working at the particle scale, so we're going way down in scale, we're often very near the limits of detection for the instrument. So with working with high-speed cameras, for example, we have to characterize and actually subtract the background noise on the CCD in order to really get a clear view of the particle cloud. So the figure to the right here, I just stuck in here as an interest piece, but it basically summarizes measurements of the kinetics of dust particles moving through the tunnel. And these dust particles were produced from autoabrasion of about 20 grams of aggregates released upwind. So we're basically trying to look for a needle in a haystack, as we would say here in Canada. It's we're looking at a tiny amount of particulate. The count rates are low, but with a lot of filtering, we were able to isolate the phenomenon interest and really begin to understand how dust disperses in a turbulent flow. And so newer technologies can provide superb sensitivity, but also there's noise to deal with as well, and sometimes even more noise the more sensitive the instrument is. And as we all know, Aeolian transport is a highly stochastic process. So we have to somehow intelligently separate the noise from the inherent noise or variability in the phenomenon itself. So that's certainly a challenge. And then regular calibration and intercalibration is absolutely essential in the work that we do. Just because a sensor looks high end and we spent a lot of money on it doesn't mean that it's going to perform well in a given setting. And we often intercalibrate between instruments. So we calibrate between the LDA and pitot tubes, which are much simpler, but I'll trust a measurement from a pitot tube over an LDA measurement. That you've got a lot of choice in the settings with an LDA, and there's a kind of a lot of experience and judgment that goes into getting measurements that are of high accuracy and resolution. And calibration further allows us to use instruments in applications for which they were never intended, and to operate them well outside their normal recommendations from the manufacturer. So I do a lot of low temperature work, and if you look at the manual, they say don't use them below 0 degrees Celsius, and of course I merrily go off and do that. But we don't do it without being very cognizant of the risk in doing that. And we do a huge amount of calibration work. And sometimes that calibration work can take much longer than the experiments. But this is where cutting edge research really happens. When we can make really novel measurements that were previously unimaginable using the tools available, that's when we advance our science.
And I guess following on from that, that's exactly what we've been trying to do with the TLS, which is basically trying to actually enhance that noise and use the noise that anyone that wasn't an Aeolian geomorphologist would be trying to filter out and get rid of because they're just interested in the surface. Because we get backscatter from the particles that are above the surface, we can very interestingly try and capture something about the sediment transport that's going on above the surface as well as the surface itself, which you can see on just this raw data in the bottom left figure here. The trick here is we do have very, very noisy data, but how do we separate out the noise from the signal? And what just is classed as our saltating grains versus what's moving below those saltating grains. And that's where, just like in the wind tunnel, a lot of work goes into not getting the data itself, but then processing that data and trying to come up with different ways of processing, which we're going to talk about later in this talk, how the wind tunnel could help with that. But basically what you can see here is a simple filtering technique to try and separate out different returns by their angle that they make between themselves and other grains, then allows you to fully process this mess of a noisy signal and get something that makes sense. So here you can see on the top right a graph showing shear velocity versus maximum saltation height. And you can see in the orange line, we've got sandy rippled surfaces and the saltation height doesn't change very much and matches what ComSort modeling predicts it should be. But on our moist, harder surface, grains are bouncing more energetically, and so they're increasing their heights as you increase your shear velocity. But it's not trivial to get from part A of the raw data to part C of the process data, and this is a real challenge where more work is required.
Okay, so we've addressed a few challenges, but there are more. Okay, so some of the challenge involves communication, or to be specific, the use of terminology. And in selected instances, I'd like to suggest that we may not even be talking the same language. And imprecision in the terminology can lead to confusion when we're trying to compare data sets. Okay, so in the interest of time, I'm not going to go through these in a lot of detail, but I'll hit on a few selected examples. So let's start with the boundary layer. Field scientists are dealing with what we call the atmospheric boundary layer. So it is far more complex than what we see in wind tunnels. There are thermal effects, convection, large-scale eddies, a lot of secondary flow. You don't necessarily have control over the fetch conditions in the field. So you may have a sequence or a change in roughness over space in which the boundary layer is still adjusting. And what you're measuring way up meters on a tower in terms of the friction velocity or shear stress may not actually be the same as the tractive shear stress that's propelling grains along the surface. So a lot of complexity there. In wind tunnels, we have different issues. We have more idealized flow, so we can easily identify the constant stress region, the outer weight flow, the free stream velocity. We're not dealing with issues of atmospheric stability and convection, unless we attempt to do so, and we have. We're not looking with large-scale eddies coming from the outer flow and so on. So the flow is certainly more idealized, but less natural, okay? And the constant stress region, you know, generally is in the order of maybe 20 to 30 centimeters in the tunnel. So it's much thinner than what you see in the field. But when we're comparing data, we tend to kind of forget about this sometimes, and it's really an important point. And it comes back to what I was saying earlier about a wind tunnel is effectively a physical hardware model. And a model is always a simplification of reality. So we're looking at aspects of the boundary layer flow, but we're not capturing the full range of the phenomenon. And as we continue in our work, we try to build in more complexity, but we have to understand the fundamentals first. But I hear a lot that, well, your boundary layers don't look like anything we see in the field, and they don't. And there are important reasons for that, and it's not necessarily to our detriment. Okay, when we're looking at threshold, if you look at it in terms of the force balance in physics, it's pretty obvious what threshold is. But as you all know, when we try to measure this, we use a range of equipment approaches. It depends on a lot of choice and decision made by the researcher as to what they determine as threshold. And then when we try to pull all that together to compare data, obviously there's some issues. And then moving on, physicists, modelers, and people like me that work in labs tend to be very precise in our language concerning the mode of transport. And we're very careful to distinguish between all 5 modes shown in this figure, from creep through reptation, saltation, modified saltation or intermittent suspension, and true suspension. And we measure these and isolate them in the work that we do. Now, when we're working in the field using sand catchers and traps, we don't make this distinction. We talk about the sand transport rate, and sometimes we just say, well, it's mostly saltation, so we're just going to call this a saltation trap, and this flux is saltation. And then when we try to compare measurements between field and lab, we start to run into some problems, because my version of saltation is not necessarily someone's view that works in the field. And specifically, when you're working in the field with large-scale eddies and a lot of turbulence and lift, there's potential to intermittently suspend particles. We don't see that in the wind tunnels, so not surprisingly, usually wind tunnels underestimate measurements of the saltation rate that we get in the field. And finally, though it may seem rather trivial, the reference level that we use in measurement can be a dodgy thing to figure out. Now, in wind tunnels, we often have a flat ideal surface, and so the surface in our analyses are the same as the bed surface. But on surfaces that are covered with ripples or protodunes, like Joe and many others study, we might choose to use the reference level as the surface or the crest of the feature. Or for surfaces covered with vegetation and large reference elements, the plane of zero displacement. And perhaps the most challenging situation arises, and we do deal with this issue a lot in the lab as well as the field, is when we have very high rates of sediment transport, and we're looking at that in high-speed photography. The bed actually appears to become fluidized, and the saltators actually impinge on a carpet of particles moving along in creep. And then where do you draw that line for the surface when you're making reference measurements?
And that in itself makes it incredibly hard to compare what we're getting in a wind tunnel versus what we're getting in the field.
Yeah, but it's not all bad. Okay, we don't need to throw the baby away from the bathwater or just yet. But I think we need to look at scaling, all right? And so in a bold leap of faith here, Joe and I have attempted to loosely identify the scales over which various measurement approaches operate. And not surprisingly, those working in lab settings do so at the smallest of temporal and spatial scales. Field workers fall somewhere in the middle of this diagram. And then we have colleagues using instruments and analyses that fall within the realm of Earth observation. And if I were to retool and start my career over again, which is kind of unthinkable at this point, I might actually start here. I think that there's some really great work going on at this scale, and some really impressive talks were delivered at ICAR by this group, and we really hope to see a seminar delivered soon on remote sensing technologies. So I don't know if those talks are in discussion, but consider it. I think it's important. So when we assign various Aeolian transport to these scales, these phenomenon, it becomes clear that there certainly is room for overlap and fruitful collaboration. But there are also research questions that are primarily amenable to a single methodological approach. So in lab wind tunnels, it's clear that technological developments have actually pushed us further and further down towards the left-hand side of the diagram. Okay, so we're facilitating very precise high-speed measurement, and this supports a reductionist approach that I've talked about before. But this movement in this technological progression is actually taking us further and further away from what we talked about 38 years ago, is the need to have more synergy and overlap between workers in the field and workers in labs. And that's just the reality. And finally, I'd like to actually acknowledge the work of modelers here. We're not going to leave you out. You're tasked with the very difficult work of using all of our measurements to try to help validate and calibrate your algorithms, often having to transcend scale, whereas we just get to say we can't do it. So I really think there's some potential here to investigate that as well. Okay, back to you, Joe.
So Cheryl and I just wanted to pull out a couple of examples where we think this intersect could potentially happen, and I guess where the most fruitful collaborations between wind tunnel and field scientists lie. And those from the previous diagram relate to things like ripples and indeed measuring saltation above those ripples or different surfaces. These two examples are areas where the spatial scales that we can fit into the wind tunnel map to some degree onto the processes that we see in the field, along with the kind of temporal nature. So they're not things that develop over a long period of time. They're things that we can get to grips with. And if we think of ripples, certainly you can see a nice example here in the wind tunnel of some ripples with mixed grain sizes forming. This is a planform looking down on those ripples actively forming, with red grains a different size to the sand colored grains. And in comparison here, we see some field data with a TLS measuring the DMs of the ripples forming, growing on a surface, getting bigger and migrating through time. So this is an area where potentially things could overlap. It just looking at the two planforms, we see some synergies, some similarities between them. But when you look at what previous researchers have done and tried to compare some of the dynamics of ripples in the lab to ripples in the field, again, there's a mismatch. But maybe here is some potential for us to try and close that mismatch and think about designing some more clever experiments where perhaps the grain sizes are matched and the wind conditions and so on, which we're going to see in a moment, are matched. Or even the fact that if we look at this field example, we see accretion happening in the field that you wouldn't necessarily be mimicking in your wind tunnel. One area where we think wind tunnels can really help in kind of the current issues that at least I see with laser scanning and field work is their ability to really get to grips with much smaller temporal and spatial scales than we can see in the field. And in that doing so, they can help us better parameterize some of our filters. So you can see here on the right-hand side, 3 characterizations where we've tried to separate out TLS backscatter data into whether it's saltating grains or a combination of surface creeping or reptators in red. And you can see just by changing the angle of the filter that we apply between 25, 35, and 45 degrees, we change which population our backscatter data appears, whether it's classified as a saltator or a non-saltator. If we go to the wind tunnel, it's much more easy than it would be in the field to then try and use something like PTV to work out the trajectories of grains and grains and work out exactly what those angles might be. What are the trajectories? What are the takeoff angles? And the and then help to use those angles distributions perhaps to better filter and better characterize the data that we're getting in the field. And finally, I think possibly the best example of where we could perhaps come together at this intersect is just thinking more cleverly about what exactly are we measuring in the wind tunnel versus what we're measuring in the field. So here we've got, as I showed earlier, but a different example this time, of a 3-minute TLS scan, and you're looking with the color map at measure of transport at height above the surface through time. You can see there's quite a lot of transport happening at the beginning, and then on the latter half that transport drops and then it starts to pick up again. If we were thinking about a wind tunnel specifically, we might not be able to capture those full dynamics. But when we look at the PTV data, we see that in the wind tunnel, most of the grains are moving within, say, 2 centimeters above the surface. If you look on this right-hand figure, the concentration of grains is quite close to the surface. So perhaps we need to do something clever, and rather than looking at our full suite of field data, take our field data and look at the points in time when all of the data that we're collecting across the surface is similar, representative of something from 0 to 4 centimeters, for example, or 0 to 2 centimeters, and take that field data segmented and compare the segmented data that better matches what the wind tunnel is measuring, and then maybe we won't have such a mismatch between our field and our wind tunnel measurements.
Okay, so we're moving close to wrapping up on this, and we're going to talk a little bit very briefly about what's on the horizon.
So I guess for me specifically, from a field perspective and measuring transport, one of the limitations of using a TLS where it's good at getting a vertical measurement, it's still quite slow horizontally, and so your temporal resolution is quite curtailed. So if we could have 3, 4, 5, 10 laser scanners operating at once in line modes, for example, then we cover a better spatial area over the same temporal area. And so then we can see some of the higher resolution dynamics that are perhaps possible in the wind tunnel.
Okay, so we've talked a lot about PTV here, maybe more than what you ever wanted to know. From a measurement perspective, I think one of the most exciting talks at the last ICAR meeting concerned the efforts of Christy Swan and her colleagues to actually carry out PTV in a field setting. I can't imagine the difficulty associated with trying to do that. But I think there's real power and potential in the future for moving some of the instrument measurement capabilities out of the wind tunnel and into the field. And this is one example where I think it's really leading edge. And hopefully with the development, the continued development of new technologies, we'll have this opportunity. So take the instruments out of the lab and make them run in the field. That's the bottom line. I think that is something that will happen. It's just a matter of time. Okay, so let's talk about active grids for a minute, and probably you've never heard of them. Active grids are used for turbulence generation, and they're now widely used in clean air tunnels for studying fluid dynamics. And basically what you do is you put this active grid at the intake of the tunnel, if it's a suction type tunnel, in front of the fan, if it's a blower type tunnel. And basically, you're closing off and choking the flow in specific areas and forcing it through other openings. And basically, these little rotating panels are connected to a series of actuators, and then the flow field is programmed or essentially orchestrated. And in some cases, it can be made purely random. So to the best of my knowledge, no sediment wind tunnel used in sediment research is similarly equipped with this at the present time. But the advantage of this technology is that we should be able to generate winds, move away from these very idealized flows to generate winds that are more characteristic of the complexity of nature. So as I said, we've got to get the basics right first. We've been doing that for decades before we can look at something more complicated. But I think we're getting there. And I think if we do this, we'll be able to sort of really start to close in or squeeze that gap, separating what we're trying to model in the lab versus what you're measuring in the field. Now, these things, again, are extraordinarily expensive. I've looked into it. It's not within my budget right now. If anybody wants to send me a Christmas gift, I'll gladly accept one. But I think they're coming. And I think that this will really provide us with some power. And as Joe talked about, it's really heartening to see that under sort of more uniform flow conditions in the field, we're able to match the height of that saltation layer that she's measuring with her TLS with what we're measuring in my lab. That's really exciting. But then there's lots of times where you get a streamer coming through, and and then that sand cloud just picks up. I think that if we start looking at active grids and things like that, we'll be able to capture some of that activity in the work that we do. Okay, so I've got a nice picture of from the last ICAR meeting and all these smart, talented people here on the screen. And it's really hard for us to predict exactly what's on the horizon or fully capture what's in place. Now, this is kind of a talk from our perspective. And we provided a bit of snapshot of the technologies, but there's always a risk that we've overlooked a major development. So if we have, please let us know. We look forward to hearing from you, as indeed the rest of the community. So as we've outlined, the Aeolian research actually extends over as many as 9 orders of magnitude in scale. That's a lot, okay? And the underlying processes are really very complex if we really start to study them at a high level of detail. So collaboration across a range of methodological and technological importance is really important for advancement of our science. We can't just use one tool to capture that. But as we've kind of hinted at, and Joe did a good job of this, is the collaboration must be intentional right from the start. And with forward planning and a lot of careful coordination of their design, we can achieve a lot with experiments that we run in the field and the lab, and then up with some really complementary and fruitful data. But by far and large, we don't do this. Okay, we're pretty busy with just figuring things out in our own domain, let alone having a conversation and say, let's start an experiment in which we're going to pair between field and lab. Now, I know there are examples where this has been done. I know of that work, but in general, we don't do that. And it's really difficult for all the reasons that we've talked about today to pull data from the field, data from the lab, where there's been no sort of coordination of effort, and then try to match things and come up with a synthesis of information. It just can't work that way. So back in 1986, 38 years ago, our colleagues identified a challenge and threw down the gauntlet that we need to make some improvements in how we work. By far and large, I think, disappointingly, Joe and I've kind of pointed out that we haven't made a lot of progress with this. And in some cases, the gap is widening. And in some cases, it's driven by the technologies that we work with. Today, we've tried to give you a bit of a progress report and a little advice, but I'm really optimistic. I think that newer technologies will come that will help us identify some of these gaps. I see this talented group in front of me, and I think there's a lot of intellectual resource there. All we need is the collective will to make it happen. So thanks very much for joining us today. I think we'll wrap up there and let the organizers coordinate some questions for us.
Virtual applause, I think. Thank you very much, Joe and Cheryl, for sharing these. It's almost over an hour of knowledge here, and it's a bit unfair, I suppose, that we have two speakers squeezed into 1 hour, but you did really well. Thanks for that. The floor now is open for questions. Please.
Yeah, Philippe, you want to start with yours?
Sorry.
Yes, just to show how the other should do. I put a question, but also when you said, Cheryl, well, Joe would dream to put a TLS in my wind tunnel, but it's too small. You need 8 meters to do so or something. So I don't see what. I understand that if you buy a TLS, which is planned to work in the field, and you cannot put it into the wind tunnel, but why not using the very same measurement technique, the very same technology for building a lab scale TLS? So is this that you can buy, or you could make, or is it something you can imagine at least?
Yeah, that probably falls more in my domain. Building a larger wind tunnel would definitely resolve that, and maybe we should go that route. And there are large wind tunnels around, lots of them, in which we might be able to convince someone to let us put particles in. So I'm not saying it's out of the question. From a very practical perspective, when we run an experiment, we're lifting and moving tons of sediment, even in a tunnel my size. And when you get to very large tunnels, and I've actually tried to do this once with a whole group of engineers, actually, just the manual expenditure of labor and energy to try to put in huge amounts of sediment into a large tunnel can be an issue. But it's a good point, and it's something that certainly should be considered and potentially doable within even a short time frame.
Okay.
Thank you. There's a question by Peng Liang, written in the chat. That's quite a long story. I think that what it comes down to is that he's interested in the progress made in parameterizing Aeolian sand transport rates related to field measurements and lab experiments, and also how moisture content affects sand flux. And the question is, could you share some new progress or data, the linking precipitation to sediment transport rates? I think that's maybe part one of the question.
Okay.
Sure
Joe, you've been working on wet surfaces.
Yeah.
Do you want to? Yeah.
So I guess it's not there's no easy answer. So at least from our kind of fieldwork, we've been looking a lot on transport rates over moist surfaces, but surfaces where there is dry sand upwind moving and feeding onto those surfaces. And there it's the kind of behavior of the surface itself. So the kind of momentum transfer of the grains means you effectively get higher bounces, higher saltation rates on those moist surfaces than you would on a sandy surface. But that doesn't really answer the question of what happens when you've got precipitation, because there, I guess the whole of the surface is getting dampened, so you're going to cut off that sediment transport incoming to your system. So it's not a trivial thing to do, and certainly I think there's more experiments, but that's something where I guess there is a lot of potential for overlap between the wind tunnel and the field. So Cheryl and I have been looking at some ways where we can see at least the physical behavior of the grains in the wind tunnel versus what we're seeing in the field, and trying to match some of those vertical profile behaviors that change as your surface gets more moist or not. Yeah.
I think that's a good point, Joe. And if you look at in the literature, there are snippets of that information. I mean, people have done experiments on raindrop impact and particle transport initiation, particularly in the coastal side of things. We published a PDV paper about a year ago looking at kinetics of transport over damp surfaces. So it's hard to find it because it's kind of scattered all over the place. But if you contact me, I may be able to send you some of the links to those papers. And I've actually got a graduate thesis sitting on my desk that was completed last month, and it'll be a little bit of time before I can get it out, but we were looking at transport over frozen wet surfaces and looking at the kinetics. There's some interesting stuff to come.
Charles is raising their hand. Do you want to unmute and ask your question?
Maybe you can flip on your camera as well. Yeah, thanks.
Yes, hi. Yes, thanks a lot for this great presentation. So you spoke a lot about the saltation and the saltation cloud, and I was wondering if you have any tips for the suspension and the smaller particles, and also if you expect the difference between the wind tunnel and the field experiment to be pretty much the same.
Yeah, so yeah, I sort of made a point of saying that when we're in a tunnel and we don't have large scale eddy motion and secondary flows, that we don't have sufficient lift to move particles up into intermittent suspension, as you do see in the field. So I pointed to that as an area that we really have to address. I don't know if Joe can see it in her TLS data, if she can isolate the difference between intermittent saltation and sort of classical saltation.
Yeah, I mean,
good question.
So certainly we get returns of 1, 2, 3 meters from the laser scanner, but there's no real way to tell the particle size from the laser scanner. So it would be hard to say this is what type of grain it was. I guess the intersect might lie on the very beginning. So you certainly in the wind tunnel could kind of look at thresholds and things of those fine particles. But yeah, going back to our diagram of the different scales of the processes, even in the field, you'd probably want some way of capturing that. I guess a lot of the kind of examples we were talking about here were focused on sand-sized particles because they're the easiest ones, I guess, to measure in the field as well to some extent. If you're putting a physical track out, mostly people might focus on the lower 0.5 meter to 1 meter, and again just from measuring some of that modified saltation, we certainly detect grains that are bouncing higher than that under strong winds on moist or gravel surfaces, and not so much on sandy surfaces. So it depends on the experiment that you're conducting. And I guess if you're looking at much finer material, you might be able to make an experiment where you could try and detect that material going up into the atmosphere, but it would take some clever kind of maybe some better ways to filter out the particle size of what's going on.
Yeah, I think that's something to consider. And let me give you kind of a field-based response to that question. You probably wouldn't expect from me, but working in the Arctic where we have really super strong katabatic winds, We actually measured not very, very coarsely and qualitatively in some cases, examples of the suspension of pea-sized particles up to 3, 4, 5, 6 meters above the surface. There's no way they're traveling in, in classical saltation. They are absolutely suspended during some of those really high gusty winds. So, this idea that suspension is limited to tiny silt-sized particles, I don't think that really holds in some situations in the field, and that we can see larger particles entering either some sort of intermittent phenomena or in full suspension, but it occurs under pretty extreme conditions for sure.
I guess it's a little bit more of a comment than a question. It kind of sounds like for the ISAR community that maybe like a great thing that we can do maybe at the next ICAR would be to have a very specific workshop that kind of addresses what you, Cheryl and Joe, are talking about, whether it's for graduate students or anyone, but just what if we actually did a field wind tunnel collaborative experiment that also maybe trains our new students like in both types of instruments, technologies, approaches, but also maybe starts to ask some of these questions and maybe start to get preliminary answers, but maybe a very rich data set that we could share and many people could work on. I guess just curious on your thoughts of, it seems like we were called to do this, and maybe we should do this the next time we're all together.
Yeah, certainly. I think there's some clever ways that you could kind of redesign both when you're designing your lab experiments and the field ones as well. So just kind of having more of a awareness, I guess, on making them so that they'll be comparable. Certainly the recent kind of discussion Sarah and I have had of can we compare some of the wind tunnel data to some of the field data that we have, and if the experiments had been set up different in either environment, then it would have made it a lot easier to compare what realistically we should be able to compare, but maybe not in the way that we've set up the experiments, because that wasn't the motivation behind them. So good. It would be good to have some experiments in the future where that was the motivation, I think.
Well, oh, we have another question?
Yeah. Please go ahead, Liam.
Yeah, thank you. I have a maybe a very stupid question, but I just wonder. I know that in nature environment, actually, wind speed distribution along the vertical actually follow the law of the wall. But I just wonder, the wind in the very small, like the macro wind tunnel, like a 10 centimeter diameter tube, is it still follow the law of the wall? For example, if we have a wind speed in the tube around 3 meters per second, can I convert it to the natural wind speed based on the law of the wall?
Yeah, well, shearing flow in a wind tunnel or along any boundary always, if it's ideal without other complicating things that are thermal, always follows the law of the wall. But you're right, scaling up from something very close to the surface to, much larger flows out at several meters away from the surface. That is something that we try to do using the aerodynamic roughness length, but often the length scales don't match up very well. So we're looking at fairly smooth surfaces in a lab setting, whereas when you're in the field, the aerodynamic roughness length is more reflective of the entire setting. And so, you know, trying to scale up, taking into account these differences in roughness length and how the flow is responding is certainly a real challenge.
Okay, thank you.
All right, thank you very much. I have some more questions, but I think for the sake of time, maybe we should wrap up this seminar. And before I have some more announcements, I would like to thank the speakers once more. Joe and Cheryl, many thanks for an excellent presentation. And, virtual applause from here. And for the seminar series, we take a little break. But actually, it's shorter than expected because we'll be back in August already with a new seminar. We haven't set a date yet because the speaker, we don't know when, but probably the first week or maybe the second week of August. We'll keep an eye on your mailbox. We'll let you know. In addition to that, we can announce that this week or maybe next week, soonish at least, there will be a new ISAR newsletter with lots of news. So please keep an eye on that as well. And if you have any other issues or questions or ideas, suggestions, please don't hesitate to contact us. Put the email address in the chat. And hope to see you soon, either virtually or in the field. Or
Thank you again, Cheryl and Joe.
Maddie, you have maybe something to add, or?
I think that was everything. Oh, we did. On the call today is Alex Hall, who was the winner of our graduate student honorarium position.
All right.
Alex, welcome to the ISAR board. He's going to be helping us with all the many things we're hoping to accomplish this year. There's Alex. Hello. But yeah, thank you, Philippe and Jean-Bernard and Andrew Gunn, who's not here, for doing such a great job of organizing the talk so far.
Thank you, everyone.
Thanks.
All right.
Thanks to everyone. Yeah, thank you for getting up at all times of the day to hear this talk.
Thank you.
Really appreciate it.
All right, I think Jean-Bernard, you can finish the recording and yeah.